Thank you so much for the invitation. So today I would like to give a presentation on some of our recent results and the consideration for next steps. AI in medicine is such a big topic, and we necessarily focus on medical imaging and image analysis. As we all know, medical imaging is a major area of deep learning applications. Since 2016, my group has been actively working in this area. Very recently, I did a scope search. So in the field, article title, abstract, and the keywords, and we use this rule. So deep and network star and tomograph star and image star and recon star. So this pretty much see how many papers in the field, and as a result, we got over 3,000 documents found. So this is a plot. So number of documents by year, and we see this is a fast growing area. And so see this slope a little bit reduced, but I did a calculation based on the number of documents so far this year, and by end of the year, we will still have increment. It's not exponential, but kind of super linear, will increase something like this. So this is already a well established area. Deep imaging papers cover different fields. For example, medical imaging, naturally, medicine is involved, and we need computer science, engineering, physics. So this say cover majority of the pie. So we see deep medical imaging is a interdisciplinary area, and in this area we can also check document by authors. So so far, and so my group. And so this is my name. My group published most of papers so far. In today's presentation, I will mainly cover 4 parts. The first is introduction to so-called foundation models, very big models, and we will see more later. In the second and the third part, we talk about the 2 application cases. One is using foundation model called M3FM for lung cancer CT screening and the related tasks. And the next is Poisson flow foundation model. We call it PFCM Poisson flow consistency model, and applied for low-dose CT denoising. And finally, we discuss relevant issues and talk about the future research direction. So first part, introduction to foundation model. What is a foundation model? Initially, we call foundation models large models. When the model becomes very, very big, and we see some emerging capabilities handling complicated multiple tasks. In last year's deep reconstruction workshop at Yale, and my group presented some initial results. In that workshop, our group gave this presentation, and we say deep learning, DL, now means diffusion models and large models. Actually, both diffusion models, diffusion type of generative AI models, and large models, large vision language models, all these can be foundational model, the foundation model. So that means the model can be trained and adapted for different tasks. So this is somehow very powerful. Why AI deep learning foundation models, so these data-driven technologies so powerful? We don't have a thorough theory yet, but we do have some understanding. So on this slide, I try to reuse Newton's second law, F equal to ma. But here we try to explain fundamental ideas behind the foundation models. So we say foundation model F equal to MA. M means masking, so some masked autoencoder. Next, token prediction. That is very, very powerful. And also A represent attention mechanism. And together we have transformers as a backbone. We can build foundational models. M equals MA is easy to remember. To get a deeper understanding, and there are many, many papers to read, and I just select 3 exemplary papers. The first one, foundation models for generalist medical artificial intelligence. This is kind of perspective article. So foundation models explained here, and you can call it a large model or universal model, but this is a name right now getting popular. And also this paper, masked autoencoder, a scalable vision learner. So this is a very good paper, show how you block something and let machine data-driven algorithm figure out what you blocked, kind of predict next token. And this is a very effective paradigm to learn representation. And the third one, probably most famous, attention is all you need. So these three papers, so FMA, very helpful understanding the secret behind the power of large AI model. In our formula, F equals MA, M stands for masking, which really means to mask and predict words. This procedure is extremely powerful, leading to so-called embedding. So you got input text, all of this. So through the word to vec, and we will mention more word to vec next slide. A data-driven program, then we can give each word a embedding. So each word will be converted to a code and a vector and with semantic meanings. So shown here. There are two methods to do this embedding, mask and predict words. So one way you mask current words, okay, and then you can just use the current words and to predict the context. So this is so-called skipgram method. So see here, use current word W to predict its neighbors. On the other hand, you go other way around, called continuous bag of words. So use the context to predict the current words. So these are two typical methods to produce word coding or embedding. The word-to-vec program shown on the previous slides is further illustrated here. So for the input text sequence, given the current word, in this case, chased, okay, given the current word, your task is to predict the neighboring words. So for example, at this location and that location, what the word should be. The process is that we assume the word chase has a intrinsic, semantically meaningful vectorized representation called embedding. So we use a neural network map the word to this embedding. Based on this embedding through network-based classifier to predict the neighboring words. So this is a data-driven method. We have a lot of text files. Given any current word, you know neighboring words. So you just do data-driven optimization. And eventually you find effective word embedding that can be used for context prediction. So this is the overall idea. As I said earlier, embedding is semantically meaningful, much better than naive encoding, like one hot vector. Say the word, you can easily encode every word in the dictionary. Say first word, second word, third word. This is a naive way, not meaningful. Embedding gives you semantic meaning. Once you have embedding, and you can consider attention to neighboring word based on similarity. The real mechanism called attention, and just use some heuristic computation to decide how much attention current word should pay to each neighboring word. The formula shown here and involving so-called query, key, and value. So say here Q, key, V, and a kind of complicated, particularly shown here involves some normalization. Q, key, V are derived or learned from embedding. So you see you got a corresponding neural network. And we extract Q, key, V is for convenience. So these additional features and will help analyze information more effectively. So let me give you an analogy. So if I go to library to find a book, I have specific ideas about what I'm looking for in the book. So such specific ideas can be considered as a query, okay? Then each book in the library has associated keywords. So these keywords corresponding to keys, okay, that describe its content. I compare my idea or query with the keywords or keys of every book to find the best match. Once I find the best match, I retrieve the actual content of the book, which is the value. So this is just a rough analogy. I mentioned the comparison. How do you compare two embedding vectors? Then you got two vectors, okay? The vector A, vector B, you got n dimension in n-dimensional space. And we can compare them in terms of so-called cosine similarity. The formula just defined here. Say the corresponding components, A1, B1 multiplied together. And so A2, B2 AI, BI, then added together. This is called the inner product, then normalized with respect to the vector norms. So on here. Then this really give you a very reasonable similarity measure. And geographically, and you got many target, and you want to match which target is this one. You just keep doing moving average across your image. You think this orange part positive one, so gray background negative one. Then you think this template matching over the whole image field. If and only if this template covers the target completely, then 1 plus 1 multiply 1 give you 1, minus 1 multiply minus 1 give you positive 1. So this cosine similarity will take a maximum value if and only if the template here you can consider as vector A, this target as vector B. When they fully overlap, this cosine similarity will reach maximum. This is just the geometrical picture. Attention mechanism is important not just within the same domain, like image domain. Attention can be applied across different domains, like across different modalities. For example, text and images, and can be encoded into embedding. So here you got image embedding, you got text embedding. They can do cross registration or alignment. And this is a very important work, so-called contrastive pre-training. And the results will be very powerful. You can just process text and visual information in a unified framework. The early form of machine learning or deep learning is so-called supervised learning. You need to have a label. Once you have a label, a neural network can learn to match the label, therefore can do the tasks you assigned to the network. But the labels are very expensive, and in many cases, labels are sparse or even not available. So self-learning or unsupervised learning, weakly supervised learning becomes so important, particularly for medical imaging. So now we learn embedding and we learn the attention mechanism. Once we have embedding and attention mechanism, we can build interesting network architectures so that we can extract even higher order features for more complicated applications. So this is an example. So you have a bunch of original images, okay, and some say pathological images. Normal and others may contain benign or malignant tumors. And then we don't have labels, okay, or we don't have resources to label all of them. So-called self-learning is based on a very smart idea. So you got an original image, okay, you just rotate it a little bit, scale it a little bit. We call it data augmentation. You got these augmented copies, and these are supposed to be very similar and the same type of image. Likewise here, and on top of the image, we have feature extractor using neural network. We got features here. Then the heuristics is that the features extracted from augmented counterpart, like this one and this one, these two features should be very similar. We say pull representations closer. This self-learning is representation learning. Likewise here, so you pull features closer. But the features and features you see here and the features you see here, they should be different. You connect them with right arrows. That means push representations apart. So this is a high-level consideration. But through this kind of pre-training experiments show we can effectively extract application-specific high-level features. So this is a very effective way for machine learning. Okay. This is a self-learning idea. These ideas can be applied nicely, so you can build the very powerful network architecture called transformer. And with the attention mechanism, you can attend to features far away from current time point or location. You can build global relation, and you can do so iteratively. So this is a transformer architecture, and the transformer can be trained, pre-trained using self-learning, and can be trained on text files or image files, audio files, everything together. So this is just a very active research area. We use transformers as a building block, many kinds of transformers dealing with text, image, audio chips, and you can have embeddings, different kind of input. So I put in different colors. So you got this sequence, say video file, text files, all of things, input into transformers. Each transformer can have many layers, and you can have many attention subnetwork, call it attention heads. So many things integrated together like a big building. So you got many experts working together. Maybe this is one layer. So you pay attention to different things from different angles, and you got processing. You report to upper level based on you process the result, and second order analysis is performed here. And you can have several big systems working in parallel. So all this information eventually integrated output predictions. So this is a very powerful network model. And when you apply this mechanism to application domain, then we say you construct a foundation model, because in that domain you can deal with different tasks using diverse data set. So this is just a rough idea. And we mentioned embedding attention and the transformer then to foundation model. It's just a rough idea. Now we are ready to start the second part. M3FM defined as a medical multimodal multitask foundation model for lung cancer CT screening and related tasks. Given the limited time, and I will only explain brief idea and the key results of our M3 FM model. For further detail, you can check our lab website and AI-based X-ray imaging system lab. You see publications here. You click publication. You will see a list of our recent papers, and this one is most relevant to the second part. And we have a archive paper entitled Specialty-Oriented Generalist Medical AI for Chest CT Screening. And we use so-called M3FM model to do the tasks. Earlier version of this work was reported in the aforementioned Yale workshop, Deep Recon workshop. And we have an associated archive paper. At that time, the title is Multitask Learning with Large Image Text Model. And now we change name, M3FM. This is the latest version of the archive paper, and fairly long, and all the details in it. First author is Dr. Chuang Niu, and he has the major credit for this work. This is the overview of M3FM model. And you see here, you can have different kind of input. So we can handle multimodality data, CT images, and I want to emphasize we handle CT image volumes. So we have this CT vision transformer. So this is a transformer. Now here we have other transformers called text transformer. So we can process different kind of text, structured or free format text. And the transformer will give output to task encoder as input. Task encoder will do further processing and to generate task-specific multimodal embedding. These embeddings will in turn drive predictor, give you task-specific output. Large foundation model needs large data set for pre-training in a self-learning mode. And so we first need to construct a large-scale data set. So this is overall workflow for data set construction. So first we define medical tasks of interest. Then we collect task-specific multimodal data. And in the third step, we process multimodal data set, align them. And as I mentioned earlier, you can align text and image files in embedding space. Okay, last step, we perform a multimodal Q&A question and answer construction. So you got this data set for training the foundation model. Our data set is very big, so we get the public data set from NLST. So this is a huge data set. Also, Madrid share a lot of CT images. And also in collaboration with Wake Forest and MGH, we have a validation data set in this domain. And we have other data set. And we do standard network training. So we have training data in blue, and here validation data and the test data. And these are multiple tasks we covered. And we also perform some generalization study and different tasks and different aspects of network performance. I will explain more in subsequent slides. Well, most foundation models deal with 2D images. Our model can handle 3D CT images. So this CT VIT and the CT vision transformer has a capability take a chest CT volume as a whole and perform multi-scale analysis. So this is very necessary for chest CT analysis, and our technology is the first in this domain. This table compares our M3 FM model against other models, and see these blue models are really cutting edge, like GPT-4o and MedGemini. These are from big companies, as you know. And ChatGPT-4o is a generalist model, can do many things, but they are not specifically trained in the lung cancer screening area. And we train our model with a much larger data set, and so we can, in this particular specialty, we can outperform these standard models, cutting edge models, and the state of the art. So you can take a look at the table and see the number of tasks performed, the number of parameters, and all different category, and the date relevant paper first released. We are happy to say our foundation model, M3FM, achieves state-of-the-art results in lung cancer screening-related tasks against state-of-the-art. So this just visualize all the results, and the ChatGPT-4o, the best generalist model, and performs suboptimally in this particular domain. That's why we believe to achieve so-called medical generalist AI, and you should first do well with specialty-oriented foundation model. All these specialty-oriented models put together, then you can achieve generalist medical AI. Our foundation model not only achieved state-of-the-art accuracy, and also showed excellent generalizability, and the foundation model performs very well on new data set. Our foundation model is architecture, and we can make it very large and very small. So we have three versions. We call it base, large, and huge versions of M3FM. And we demonstrate that scaling low works here. The larger, the better. Just show the results. Say this black, huge, get a little bit better, and the large significantly better than base. And this is general trend. Our model also shows good adaptability. When we give the model a new task, for example, some side effect with immunotherapy, so here, the model can be easily adapted to perform the task very well. Just use a very small number of data points, then the model learns adapt to this new task. Because of the intrinsic alignment between text information and the image domain information, and the model can naturally yield interpretable results, as shown here. So we see the history of heart disease, attack, hypertension, and diabetes and stroke are highly relevant for cardiac disease diagnosis and risk prediction. Okay, now we move to the third part, talking about second type of foundation model, and for new application and for low-dose CT denoising. This foundation model called Poisson flow consistency model. So PFCM, Poisson flow consistency model. Okay. Again, this is the publication page on our lab website. And this is a review article we wrote for annual review biomedical engineering, already accepted. The title is Physics-Inspired Generative Model in Medical Imaging. So all the details in this article. And if you're interested, you can read more. Briefly speaking, generative AI becomes very hot recently. And state-of-the-art results were achieved using physics-inspired generative models, particularly diffusion models, Poisson flow models. So we did, again, a scopus search. We see this rapid increase in number of publications in this generative AI domain. I used the software tool, VOS Viewer, to see the overall landscape of the physics-inspired generative AI papers. It looks very colorful and impressive. So these figures were used in our review article. The first author, Dennis Haynes, this gentleman, very smart PhD student. The second author is a co-first author. So we have this review, and I believe this is the latest review article on this topic. Physics-inspired generative AI models can be appreciated from different angles. The first angle, certainly physical angle, and we can consider ink diffuse in water. So this phenomenon is very much well known, can be studied using thermodynamics methods and principles. So this is essentially equivalent to Ito calculus, with which we can solve stochastic differential equations. And here is the Brownlee motion. Albert Einstein once studied this phenomena. And we can similarly study stock market, random walking. So you have drift term, random term. So just capture the diffusion process. And we can describe the forward and the reverse processes. These become very relevant to machine learning. Computationally, we can consider variational autoencoder, like autoencoder. Input and output should match. So through data-driven self-supervised learning, network is trained and with a bottleneck for feature compression, and the output should match the input. In contrast to classic autoencoder, variational autoencoder replace the bottleneck feature with a latent data distribution. In this case, it's a Gaussian distribution. What needs to be learned is mean and variance or covariance metrics. So once you know the parameter, this becomes a generative model. So you just randomly sample this latent distribution, you can get output and from the same underlying distribution as the original data distribution here. Variational autoencoder can be extended to hierarchical variational autoencoder. So in generic variational autoencoder, you have a common single latent space Z. But for two-layer hierarchical variational autoencoder, you have latent space Z1. Then this serves as input to another variational autoencoder with latent space Z2. So you just can go this way, then from X to Z1 to Z2, then just go back. So this is more expressive than single stage variational autoencoder. Computationally, we can consider diffusion model-based AI generative model as a hierarchical variational autoencoder, many stage. And we can visualize the process as follows. So you got a original image X0 from a data distribution. You keep adding Gaussian noise. So you get the original image weakened step by step, noise level elevated stepwise. And eventually the image becomes so noisy, just a Gaussian random field. This is the latent space you want. And so this is a forward diffusion process. This is blue things, okay? And also can be considered as a Markov chain. And then the reverse process, just from a random field, like a variational autoencoder, you have a Gaussian random noise. You sample the noise, then you take a little bit noise away from it, the denoising process, step by step. Eventually, you recover a new sample under the same data distribution. So this is a essential idea. We know a continuous function can be accurately approximated piecewise linearly, okay? Just shown here. And on the right-hand side, there is a similar picture. Arbitrary data distribution can be considered as a Gaussian mixture, okay? Recall what we just did, we gradually add Gaussian noise little bit by little bit. This is essentially equivalent to construct a Gaussian mixture to approximate the original data distribution. This is a classic powerful diffusion model, well known as DDPM, denoising diffusion probabilistic models. And we used this model many times and received decent results. Other groups also reported successes using DDPM. And the results are so good and are often reported as beating previously very popular Gang algorithm. And now the diffusion model take over in terms of sample quality. But you know, it involves 100,000 steps gradually at small Gaussian noise. This is step by step. So the computing speed is slow. Wang's major research efforts were devoted to accelerate diffusion model. Inference speed is a big concern. And a representative work called consistency model. So instead of going 100,000 steps, in principle, this consistent model can perform inference in single step. In a generic diffusion process, so you add Gaussian noise step by step, totally blurry the original image, make it a pure random field here, okay? And when you do this with many images from a big training data set here, you have many x zeros and the same data distribution. You essentially have a probability flow, ODE. So you're moving from left to right. You got this way. And then in the reverse process, you go step by step, denoising step, take image noises away. So eventually you get the clear new sample. So in the diffusion process, you have a lot of data for training, and your purpose is clear. Any step you want to map to the original data, original image domain under the same data distribution. So we want to train a neural network. So from any step on, we can get the original image shown here. So make the whole process very consistent. So no matter you start here or here or here, you all can go back to the original image domain. That's why we call the model consistency. And this is more complicated computational or prediction task. Therefore, the training is more challenging. But once the consistency model is trained, you don't need just do small step here, step 1, step 2, until original image domain. Then any place you can just, in principle, from the pure noise, you can just jump to the original image domain. The diffusion model, DDPM, and similar models are based on thermodynamics. So physically speaking, you may wonder if any other physical phenomena can be adapted, utilized for generative AI. The answer is yes. So this is an excellent paper from MIT entitled Poisson flow generative models. In this approach, original data distribution is treated as a charge distribution. So the data distribution shown here, because the data distribution is not uniform, and we already considered as a charge distribution. Therefore, the electrical force line from this 2-dimensional space into 3-dimensional space will no longer be uniform symmetric. But if you keep moving away from the original charge distribution, far field will be very uniform. So this is similar to the diffusion model. If you just diffuse long enough, you got this uniform kind of featureless random field. So in this case, a very far field, you have a random distribution. You randomly pick up a point far away, then you just trace along the electrical force line back. You resemble the original distribution. That is a generative process. To a small degree, the Poisson flow generative model is similar to the work we did more than decades ago. At that time, we tried to digitally straighten the colon, open it up as shown here. Problem is that GI tract is convoluted. The cross section you form in flattened space that may have conflict. Our idea is to assume colon central part is positively charged. Then the force line will naturally define curved cross sections. They never conflict. So this is a near field, near electrical field, near field application, while the Poisson flow generative model is a far field application. The AI field is highly competitive, evolving rapidly. And very quickly, Poisson flow generative model is extended again by the same group. They call it Poisson flow generative model plus plus. In the Poisson flow generative model, and in the example I just showed, the data distribution is in 2D, but the electrical field, the Poisson equation, governs the electrical field in three-dimensional space. So you have one dimension augmented. Then naturally they ask, how about we augment the original data distribution space to D instead of just 1? If the increased dimensionality equal to 1, then that is Poisson flow generative model. How about generative D? And you can consider D keep increasing. When D becomes infinity, and it was proved that the Poisson flow generative model becomes a diffusion model. Then we have a continuous spectrum depending on different D. And the further analysis shows when D is small, the result will be more robust but less precise. And when D is large, the result will be more precise but less robust. And there is an optimal D star depending on application. A piece of work we recently performed is the combination of diffusion model orientated consistency model and the Poisson flow generative model plus plus. So on one hand, and PFGM plus plus give you best quality. On the other hand, the consistent model give you highest sampling speed. So we combine both, and this is the archive paper. We use low dose CT image denoising as initial application. First author is Dennis Hein, and he has the major credit for this work. That's why we call our model PF, Poisson flow, CM, consistency model. And this is potentially foundation model. It can be used for denoising, deep learning, reconstruction, and other tasks. So this initial example showing the success in image denoising, and the other work is in progress. So this is ground truth. So the top row is the denoising results using generic Poisson flow model and use many steps. Here, number of functional evaluation equal to 79, so roughly 100. Okay, then using this PFCM, just one step, so number of functional evaluation, you get comparable results showing the quality and the speed optimally balanced. Now, the last part, discussions on future research. Our first foundation model is a vision language model. Our claims are as follows. It is the first foundation model for lung cancer screening and related tasks. And we constructed the first largest multimodal question answer dataset involving over 100,000 CT scans. And we delivered the state-of-the-art performance over all 17 ILCS related tasks. And next steps include we can just generalize this model, not only for lung cancer screening, and rather for general chest CT tasks. And we can make an effort for clinical translation and eventually make the foundation models AI agent into healthcare metaverse. Also, we developed the Poisson flow consistency model as our generative model, and this represents a very strong prior knowledge on the original high-quality dataset. And this is an ideal data model and good for different kind of Bayesian inferences. And the denoising is just an example. And it also delivered state-of-the-art performance at high computational speed. And next step, we can try to further improve sampling speed and extend the model to new tasks, such as field view CT with different views, 100 views, 50 views, 10 views, and all use the same model. And again, this diffusion model can generate a new data set, can be used for imaging tasks, will be a key player in healthcare metaverse as well. AI models. Foundation models in particular are powerful, but they are subject to AI-specific concerns. We are also working on these concerns such as the uncertainty, confidence interval, generalizability, stability, explainability, security, many issues. So all these are new things, and we need to make further effort to address all of them. This year we celebrate RPI's 200 years anniversary. That means 200. To me, this means metaverse. We have a vision about healthcare metaverse explained in this article. And we see two kinds of metaverse are relevant. One is healthcare metaverse. We say foundation models, AI agent will be key players there. And the other relevant to university business is educational metaverse. And we also working on education domain. And we developed the ChatGPT for medical imaging class education. And also we developing avatar instructor to deliver medical imaging lectures. So all these things are very promising, and we see synergy between these two metaverses. And so we hope we can generate more results along this direction and find more collaborators. Finally, we acknowledge general support from NIH and major companies. Last, but the most importantly, I'm really grateful for my lab members and key collaborators. Thank you very much.